Alright, in this video we're going to take a look at detecting changes in direction. We've got a particle being born with particle draw, given some velocity, and then using the bubble motion to change its direction. So what we want to do is same kind of thing as before, and if we had been smart we would have saved that out as a black box. So we're just going to go ahead and do a quick recreate. Let's say not all particles. Actually now we're dealing with a red particle here and a yellow particle, because we want to use the yellow particles to emit whenever we detect enough direction change in the red particle. So we want the red particles to go ahead and store their current direction. And let's go ahead and do this. And so you remember, direction is a component of velocity. And we're actually just going to pull in direction. It's actually normalized velocity. Let's go ahead, or unit velocity, depending on if you speak Max or not. Max, using expressions, will calls a normalized vector a unit vector. So we're going to go ahead and take that velocity of our particle and just go ahead and store that every frame or every sample. And right now we're set to 96 samples per second. Let's actually switch that for now. Let's go per frame. So every frame, go ahead and store your current direction. And then just like before, we're going to go ahead and compare that with our current direction and compare that back in the memory history that we stored. So we're going to need an integer to access the depth. Let's get a memory and depth, and which variable we want to access is the direction. And of course we're going to need our current direction. And then we're going to need a little bit of math to do some direction calculation. Let's go ahead and look under our vectors, and let's get, what do we want? You gotta love the recording software, it takes it away there. What we want is, let's just grab a VOPS and we'll just calculate it here. So if we do a scalar product here, one vector multiplied by the scalar of another, that's going to end up giving us a scalar value based on the loosely on the angle difference. To get the actual angle, what we would do is do the acos of that. We can't have a vector output here like our VOPS has, so we need to change that. Let's add an output, just accept scalar, and remove that vector output. Expression operators don't really like it if you have extra inputs or outputs that are not being used, so always remove the ones you are not using. Otherwise there's a chance it won't fully evaluate. So let's go ahead and actually remove that acos for now, and we'll just take a look at the kind of values that we're getting. So let's get my current, and here's something else. We've got our current velocity, and if we try to just pump that in here, because it is not normalized, it's going to vastly overpower this direction vector, which is again a normalized vector. So we're going to need a normalize function. So we use the unit vector, which is how, again, Max describes normalized vectors. It's with the expression operator unit and then the vector. So let's take that off our current. So now these two are kind of in the same length space. They both have a length of 1. We'll take this, and not into the depth, but actually into, we'll call this direction difference. We don't need a depth for this one. We're just going to be using it to kind of debug and look at our values. So let's turn on debug and get our view set up here. So direction difference 1, 1, 1, 1, 1 all the time. That's not quite what we're after. Okay, well our integer, remember, was set to 0, so it's actually storing our current direction and doing a scalar product against our current velocity. So our same times our one vector who's going the same direction times another vector who's going the same direction, the scalar product of that is going to be 1, meaning that they are entirely similar. They are equal. So let's actually rename these dynamic sets. We'll call this store data, and we'll call this compare data. And you know what? In order to save this as a black box this time, we're going to create a new dynamic set, and we're going to call it store and compare. If we can spell compare correctly. There we go. And in order so that we do not lose these memory values, we're just going to drag these into here so that we don't break those connections. If we cut and paste those dynamic sets, those connections get broken. So we've got this all nice and tidy. Let's make sure we set our direction difference there. Okay, and so just looking back one time sample, the change in the direction amount is not very extreme. So let's go ahead and increase this, say 10 frames ago. Remember, our sampling is set to frame. So we do get some pretty, okay, so we see quite a dip in here. This is around 4600, and be nice to have a little calculator there to show what actual frame number that is. But you just have to start thinking in ticks, because that's basically what this is. Actually, it's exactly what that is. So let's notice, so right around, 24, frame 24, there was a major change in direction as it turns around and starts heading back. So what we're going to do then is we're going to set up well, we've got this memory here already. Let's go ahead and we'll just use this direction difference in another rule. Let's say, we'll call it have something happen. And inside have something happen, of course, the red particles are going to test their the amount of difference direction. Oops, not the input, but the output. And we want to check that with a threshold. Say, hey, if that amount is between, say, and remember, we're talking vector values for direction difference here, which goes from -1, where they're totally opposite, to 0, where they're perpendicular, to 1, where they're similar, or exactly the same direction. So we want to actually detect between, say, -1 and 0. So it has to be inside that range in order for this other thing to happen. And that thing that's going to happen is we are going to generate some yellow particles. Let's just start emitting a stream at that point. Yeah, this is all fine. We'll just hook it up. We want to just see some get created. And so because we've got the position, or the particle connected, the position born is going to emit these yellow particles wherever that red particle is right then. Okay, so here we go. And of course we're not seeing them. Gotta love it when that happens. Our threshold actually does not reach the threshold that we need. We kind of wanted to pick right around 0.29. It goes as low as 0.27. So we're going to actually have to change this. We're going to bump this up, and our edit on the fly is on, and with debug that's going to update the whole thing. So edit on the fly is great. It's just that when you end up with debug or a really big dynamic tree, it's going to slow things down. So we'll just go back to 0 so it doesn't try to update through all the frames. Let's say anywhere up to 0.28. So if the amount of direction difference is -1, so totally opposite which the direction it was going before, all the way up to 0.28 of similarity, then go ahead and emit or yellow particles. Boom. Okay, so there we get a few coming off of there. And let's actually get their direction in line with our particle there. And why don't we do a pistol shot to get quite a few more than just one at a time. So that's kind of the basics of checking direction change. What we also want to do is take a look at an example where we can determine whether a particle is, if it was heading up and then now it's going to be heading down, versus whether it was heading down and then heading up.